afternoon, everyone. So, any questions? Questions?
There's a question about 13A.
All right. Yes. There were a bunch of questions on Piazza, and I didn't have time to do anything because of the grading. So let's catch up. Okay, 13A. Yes. All right, so as a general remark, as you know, the reason we're doing this thing with the draft and the final is exactly to get these kinds of questions up, right? So this is a great question, and it is a really good idea to ask these questions now rather than Saturday morning. So that's how it's supposed to work. So let me sketch away here. So the idea of this question, the reason why I put it there, other than a general sense of torture, was to to give you another way of looking at what a hash table, what it's like. And so when you look at a hash table, you say, what do you have? You have this kind of picture that you had in the book. Where you have an array of buckets. Each bucket is a linked list. And so when you think about it a little bit more abstractly, you can say, what is an array? It really is, an array is the same thing as a map from integers. And in this case, it would be to buckets. And what is a bucket? A bucket is a linked list of objects, right? We're not we could say of type T if you wanted to, but so you could say that one way of looking at a hash table is it maps integers to these buckets. And so if you have a particular object, then the key would be the hash code, and that gets mapped to all elements with that hash code. And so that's a way of looking at what a hash table really is. What's a little weird, of course, is that a map is already implemented as a hash table. And to take out all possible confusion from that, I said, use a tree map. You don't yet know how a tree map is implemented, so you can look at it abstractly. You'll learn soon enough how a tree map is implemented. So you can view it as that, but that was actually not what the interesting part of the exercise is. So what this exercise is really all about is how to use these damn iterators. So it's an exercise about iterators. That's all that it's about. And it is kind of to see how painful it is to use these iterators in a way. And so that's why the way it's posed is that you absolutely have no flexibility in the implementation. So when you look at the implementation, so here we have our bucket map. You can't change it. You can't add any instance variables. And more importantly, the iterator, you have to use exactly like I want it. So here you have an iterator through the keys. That's what it really is, right? So the well, I shouldn't say that. It's an iterator. No, I'm saying this all wrong. This is an iterator through the linked list. So, and it's kind of the same thing as the position pointer that you have in the manual code. This thing here is the current bucket, and that is the equivalent to the index to the current bucket in the code of section 16.4. This thing here is I guess a pointer to the current thing. So actually, I'm not even sure this is true. No. All right, so let me draw a better picture. So the bucket iterator points to some bucket. So it might point to here. The current iterator, and let me make this one a little bit bigger. The current iterator points to somewhere inside that bucket, and the current bucket is just a reference to this linked list. So what's the difference between the bucket iterator and the current bucket when they really point to the same thing? They're different things. The current bucket is an actual linked list. And this thing here is an iterator, which means it can advance to the next bucket. Now, when you look at the picture, it looks like the current bucket. You should be able to ask the iterator, hey, where are you currently pointing to? And then that would give you the current bucket. But that's unfortunately not so with the Java iterators. If you remember, what was that homework where you had the pointer things? That was, I don't remember, 11C or something? So in that homework with the pointers, what I was trying to get across is that in most libraries, the way iterators work is they point somewhere and you can say, tell me where you're pointing to. I forgot. Tell me where you're pointing to. I forgot again. Tell me where you're pointing to. And you can ask it as often as you want. With the iterators in Java style, you cannot do that. And so, as it turns out for this algorithm, you need to remember where that was. And so that's where the current bucket came in. All right, so how might one initialize these? So we're making a set iterator. And now we need to initialize these three things. So what might one initialize the bucket iterator with? So to get an iterator, you always have to iterate. You may have to have a collection where you can say, hey, collection, give me the iterator. We only have one collection lying around here, and that is the map here. So surely that thing must be buckets.iterator. No, because it's a map and it's not an actual collection. For a map, there are three kinds of iterators that we can get. We can iterate through the keys, we can iterate through the values, or we can iterate through the entries. I don't think we talked about iterating through the entries in class, but it's in the book. So in this case, do we want to iterate through the keys or do we want to iterate through the values? I guess the values, right? That's the only thing that we can do. So we have to say over here, bucket iterator equals buckets dot values. Let's see, that gives us the value set. So then dot iterator. And now we want to get the current bucket. I'm not really sure whether we want to do that in the constructor or in the first call to has next or whatever. You've implemented a couple of iterators before, and there's always a bit of a subtlety. When do you want to jump to the first thing? Do you want to jump to the first thing in the constructor, or do you want to wait for the first call to has next or next? But let's give it a good try, and let's say maybe we do this in the constructor. So the current bucket is a linked list of object. So how would I get it? What's my chance to get a linked list of objects out of what I have so far? So if you look at the picture, what I want is so I'm at the beginning. So right now this thing here points points before this guy here. And now I want to capture this object. How do I get it? Bucket iterator dot next, right? Because if I have an iterator over linked lists, I want to find the first linked list, that is bucket iterator dot next, right? There's a bit of a danger of me doing this. What if the list is empty? I shouldn't say what if the list is empty, but what if the hash table so that's my current bucket. And how would I get current? Current is supposed to be an iterator that goes over the current bucket. So current is supposed to iterate over this one here, so current is supposed to go here. So how do I get that iterator? You say current bucket dot list iterator. Is it a list iterator? Yes, thank you. Current bucket dot list iterator. Okay, good catch with the list iterator, because over here it is actually a list iterator. All right, and there is a, let's see, yes, that's fine. So there's no to do. If that list happens to be empty, I get an iterator through an empty list, which is not a problem. All right, so now let's do has next. And so as a to see what model to follow, let's go to the textbook. And so we're in chapter 16. And so here we have a perfectly good hash set iterator. This bucket index is the moral equivalent of the bucket iterator. See, I can't have an index in my model because all I know it's a map. And so I don't know whether there is an array, and there really isn't an array actually. And so the bucket index and the bucket iterator are the same thing. And the current, that actually is the same thing as my current iterator. The trouble is that here in this model where I'm close to the metal, I can actually have a reference to a node. When you have a linked list in the abstract, you can't get at the nodes. The nodes are not exposed to you. The nodes are some internal implementation detail, and the closest thing you can come to a node is an iterator. An iterator gives you the current position. So over here, actually, we've set bucket index to -1. This might be a good model to emulate, and I'll leave that to you to see. Maybe you want to defer this thing here and do the action in has next. Maybe I should do next. Next seems easier because I should just be able to follow this model. So this model tells me that there are two different cases. Either the current bucket is still not exhausted. In that case, I should do something with inside the current bucket. So let's look at my picture. That is in fact my situation here. So what I should be able to do is advance current to the next level here, and then return the thing that was there. So how do I know that that was the case? That would be if current has next. In that case, I think I can just return current.next. That will jump over the position here. So it'll jump over here. And as it jumps over there, it'll return that value. And my iterator is still in a logically consistent state. It's now one further advanced in the current bucket. Now what if I'm at the end? So I'll do this again. And now I'm at the end. At that point, I'll have to advance to the next bucket. Well, how do I advance to the next bucket? In the code that you find in the textbook, that was a little bit tedious. There was a do-while loop because we had to jump over any null entries because that array of buckets could be sparse and there could be a bunch of nulls, and we had to find the next one that wasn't null. But in my case here, I'm actually in a better position because this thing here, the bucket iterator, if I ask it to go to the next bucket, it will instantly go to the next bucket. That's how an iterator works. It's an iterator over buckets, over linked lists, so it'll move to the next linked list. So over here, I could simply advance it and say this was what? Bucket iterator. So I want to say bucket iterator.next. I guess I'll put a to-do here. What if at end? So every time you call next, you have to ask yourself the question, what if there is no next? And so right now I'm just putting that here because I want you to do something as well. So, and now the other crappy part, as I never tire of reminding everyone about Java iterators, is that whenever you call next, that is your one and only chance to capture what it is that was traversed. So I have to capture the next, and that would be in current bucket. That's my chance to capture it. I'm capturing it. So now current bucket points to the second bucket. This diagram is now looking rather messy. So it points to the bucket that starts out here. And now I want to return the first element in that bucket. So that means I also need to update current. That's like this. And so you just return what's under that. And now you can save yourself a ton of grief. If you, as you do this, make sure that all of these linked lists are non-empty. Let me say that again. You can save yourself a ton of grief if you make sure that all the linked lists are non-empty, because in that case you don't have to worry at this stage here, does this thing have a next, doesn't it have a next? Because if it didn't have a next, if it was an empty list, then you would have to start jumping over empty lists, and that's just the kind of pain that you don't need. So it's easy enough to make sure that all of those lists are non-empty. In the add operation, well, you're never going to have a problem with add, right? You're only adding stuff. But in the remove operation, what you need to do is when you do remove something and then you find that that emptied the bucket, then you want to get rid of the bucket as well. And so in the remove operation, the weird thing is that remove always has to come after next. So remove always comes after next, and that means that you can still call remove on the bucket iterator, which has just jumped over the current bucket. And so this will actually work out. So if you're sure to maintain that aspect, and of course there's test cases to make sure that happens, then next is fairly simple. So there's a slight complexity in remove, that you should always remove empty buckets, but it's doable. So that's the basic idea. So I'm leaving a whole bunch of implementation details for you, such as what happens when one of these iterators is empty. I'm also, I jumped ahead here and set all of this stuff here, made it, so to speak, jump to the first position in the constructor. I'm not sure that that is actually wise. Because if you look in your textbook, that doesn't seem to be what's done there. And I remember when I solved this problem, I followed this algorithm as closely as I could because clearly it was confusing. So the whole point of this is to give you some practice with iterators and also to blow your mind a little bit when it comes to this guy here. Right? I know that an iterator over a linked list looks scary. And like with all scary things in computer science, the key is not to think about it. Remember when we had recursion? And I said recursion is actually pretty simple because as long as you only think of one level, then you say, okay, I'm computing that triangle, the area of the big triangle, and I'm just going to chop off one thing and make a slightly smaller triangle, and then I figure out how to use that. I'm not thinking about how the smaller triangle gets even smaller, or how the polygon gets chopped into more and more pieces. I don't want to know, but I just want to know one level, and then it's manageable. And so here you also want to kind of chunk about that. And every time that you read linked list or object, that's two levels, right? So you have iterator, linked list, and object. And you want to not say that. You want to say linked list of object, you just think about this bucket. A bucket is a thing, it's a pail that has stuff in it. And yeah, it has some substructure, that's actually a linked list. But you don't really want to think about that. You just want to visualize this thing here. As something that has, little rubber buckets there. Think of your typical cleaning pail there. And so when an iterator goes to the next bucket, all you want to do is, iterators are hard enough to imagine. All you want to do is to say, okay, previously it was here, now it's here. Or actually, since Java iterators are kind of between things, right? Previously it was here, then it's here, then it's here, and then it's here. You want to think about it at that granularity. So it's a super good exercise to think about these a little bit more abstract things. This is a hard problem. It took me, I think, the entire train ride. It was like 60-some minutes to do this. And I made multiple mistakes, and I thought, gosh, this is actually a hard problem. So it'll probably take you longer. So start with that early and build in some frustration cushion and do it a few times. And don't change the data structure. I will make sure that the grader finds any attempts of monkeying with the data structure or calling clone or any ridiculous things that people said that they were trying to do. So really do this in only this way and in no other way. Other questions about this? Yeah?
I was reading up the authors and you said that you can't use collections.
That you what?
I was reading up the author and there were people who finished 13A final and then they said
13B or 13A?
13A.
Okay.
And then they said that they don't know they can use the bucket.value.iterator for bucket iterator.
That's the only way to get that iterator, though.
Oh, turns out my friend had an email from you saying that you want to have the iterator like a
Oh, you know what? I remember an email like that, and I may have misread that email. Yeah, I don't see any other way of getting at that iterator. Okay, maybe your friend needs to send me another email so that I can follow up because I don't remember what I wrote. I dimly remember the email, but I don't remember the answer. Okay, other questions? Yes?
Did you use pseudocode for
13B, let's have a look. The back class. Yes, so this is pretty similar. So now we're back at close to the metal level where we have arrays of nodes. Now with the bag, each node has a data and it has a count. And the key here is that when the iterator is at a particular position, and now you want to advance the iterator, then the iterator is supposed to report this element as often as the count says. So if the count says 3, then the iterator needs to stay on this spot 3 times, and the 4th time, then it moves over here. So that clearly means that the iterator itself, did I tell you what data your iterator has? Yeah, so I did tell you what the implementation is. So you put a count field in here. And in the interest of time, I'm not going to write pseudocode, but I'm going to just simulate it. So the first time you're at this element, of the count is 1. The second time the count is 2. The third time the count is 3. Then when the count of the iterator matches the count of the node, then you really move to the next one. And set the count back to 1. So that's really the basic idea. Otherwise, it works exactly like the hash table iterator in the book. Again, in the book, I guess the difference is also that in the book we didn't implement remove, right? And now here you have to implement remove. So let's talk about remove for a minute. Let's go back to the situation where we had here. So let's say the iterator is in this position, and I call remove. What does remove do? It just decrements the count, right? It says previously there were 3, and now there's just 2. Now the only complexity is, what if this was 1? And I call remove. So now I'm going to call remove, and you could theoretically say, well, whatever, I'll just set this thing down to 0. But if you leave 0 nodes in there, that makes next much more complicated, because then next has to skip past any 0 nodes, and it's also inefficient. Right? It's super inefficient to leave these 0 nodes in there. And it makes your code more complex, so that's not nice. So in this case, you want to remove the node. Now it's a singly linked list, and you have a pointer to it, so that doesn't do you good. That's not good enough to remove it. So hopefully there was also a pointer to the predecessor, and sure enough. So this previous node is there to make remove possible. And so you also have a previous, which, oh, I guess in this case previous is null, because there was no predecessor. And in that case, you must go back to the original linked list. Let's hope that we have a position where we are in the linked list. Oh, this bag, am I stupid? Was the bag not a hash table? Was it just a linked list? I don't remember a thing. You guys implemented the bag. What was it? Was it just a linked list, or was it actually a hash table? It was just a linked list. Okay, so I can take out all of that stuff here. Okay, then that makes it easier. Okay, so this node wasn't there. Was it a singly linked list or a doubly linked list? Was it a singly linked list? So all we had was a head. Did we have a tail pointer? Or first, right? Just a first. That was all? All right. So if the predecessor was null, then we need to say first equals first dot next, and link in that. So let me just, so here and remove. I'm just going to put in code up this place, right? So we'll say current count minus minus if current, if what it was previous, equals null. Oh, if, first of all, if current is null. Current count is 0. That's the case where when I'm worried about so if previous is null, then first equals first dot next. Else, okay, I'll leave that to you. You're now experts on linked lists. But the one thing that I wanted to briefly talk about is this is inside the bag iterator, right? So we're in the bag iterator class. And over here, I say first equals first dot next. Have a careful look at the instance variables of the bag iterator. Do you see any first? There is previous, current, count is after next, at mod count. No first. What the heck's the first? See, what we're coding up is inside this class here, the bag iterator. And the first element is over here in a completely different class. Now, if you carefully looked into all of the code that you've written in chapter 16, there's a whole bunch of times when in the iterator class it accesses the first and the last of the linked list. And so this is, I don't think, something that we've really talked about very much, that when you have an inner class, notice that bag iterator here is an inner class of bag. Where's bag? Bag is up here. And it's nested inside. Just like list iterator is an inner class of list. These inner classes, they know which outer class object has constructed them, and they can access their instance variables. So this particular bag iterator here this one here, let's call him Fred. Fred remembers that it was constructed by this particular linked list instance, by some call that said new bag iterator. And that call was inside this particular linked list. And it remembers that, and every time that you access an instance variable of the surrounding linked list, it is the linked list that gave birth to it. So you've been using that, you've been writing that code for several weeks, and I don't know if you've paid attention to that subtlety. So it is a bit of a subtlety that you can use the surrounding instance variables. So that's the basic strategy that you would, next is pretty simple, has next is pretty simple, but remove is nasty. Because with remove you need to make sure that you're cleaning out those empty lists. And again, there's plenty of test cases to make sure that you do that. Questions about that? So, just want to say one quick thing about, this is 13C, I believe. Yes, so 13C is my absolute favorite assignment. Because it's something that's getting more and more important these days. So the kinds of sets that you've seen so far were mutable sets. You add things, you remove them, and the contents of the set changes all the time. The newer thinking is that mutable data structures are not all that great, because if you access them from multiple threads, then you have to lock large parts of the data structure, or bad things are going to happen. So nowadays one tries to write code with immutable data structures when one can. So in an immutable data structure, you make a new set whenever add or remove is called. And it sounds kind of crazy, because just look at the tester code. So here I'm making a new set that contains potentially 10 elements. Now I add in an element to the empty set, and I get a new set, a different set. Now I add another one, I get another set, and I get another set. So each time I get a different set object. If that set has 1,000 elements, and after I add an element, then I now have two sets, one with 1,000 elements, one with 1,001 elements. Sounds totally crazy. And why would anyone want to do that? But the fact is that as long as both sets are immutable, they can share almost all structure. So, and that's a really powerful idea that you're going to see more and more in the years to come. So right now it's still a little bit exotic, but in your lifetime this will become routine. So let's say I have this set here, and now I add one more element to it. Then yeah, I will need another array of buckets. But if this bucket here and this bucket are the same, I might as well just share them. I just have another reference to them. That means I'm not copying the elements, and all I need to do is add one more bucket here. That's the happiest scenario, where most of the buckets are completely unaffected and I just copy references to them. Of course, it could happen that, unluckily, that the element to be inserted is in an existing bucket. Then what I'll do is I'll put it to the front of the bucket, and I'll share this rest here. Huh. That wasn't actually much unluckier, right? It was just the same thing. I get to share the entire structure. So adding is always cheap. All I do is I add one more node and I can share the rest of the structure. Removing is a little worse, because what might happen is if I remove something in the middle, let's say I remove this element here, then what I told you what you should do is just copy the head and share the tail. In hindsight, that's stupid, actually, because what you could do, what would be even better, but since I already gave the other instructions, now that I think about it, is one should be able to rearrange. I don't know if you could do that. Okay, now I don't want to wing this. So maybe there's a better way, but I don't know. So, but the point is that you have the structural sharing, and it's easy enough to implement. This is actually not as hard to implement as 13a. It just looks baffling the first time that someone sees it. It looks like it's hard to believe that this would make sense. But this is the future. So you're going to be using these kind of immutable data structures more and more because they work so nicely in concurrent programs. So I thought you'd want to see that. All right, so now we've talked a long time about this stuff, and I'll give you the quick rundown about today's lecture, which is actually not very deep. So the lecture is all about trees. And so trees are, a very common concept. You've seen trees all the time. Here you have a family tree. So what's a tree? You have a root. This way, you have a... You have a root of the tree, and that's how trees work. They always have a root, a single root. Each root has children. The children themselves are nodes and can have children, and so on. This is a general tree where a node can have as many children as you like. So the root here has 1, 2, 3, has 6 children. Later we'll see binary trees where every node can have at most 2 children. So nothing much to this. So there's a whole bunch of concepts that you've seen: nodes, children, leaves, interior nodes, and they all mean exactly what you think. So like the concept of a parent is, it sits one further up. The single most complicated things about trees is that the root is always on the top. Does anyone know why? Because trees were invented by an Australian computer scientist. So for traditional reasons, one always draws the root on the top. All right. So I'll leave that to you to read through these, and we're not going to do this clicker question. Tree implementation. So in section 17.1, you're going to be looking at this general tree implementation, whereas in later sections, we're going to be looking at binary trees, and they'll look a little simpler. Binary trees are very important. You're going to see them much more than you might like in 146, but general trees are also important. They just look a little bit different. So the way that I'm implementing them here is as follows: that I say a tree has nodes, and what does each node have? It's just like the node of a linked list with one simple exception. With a linked list, a node has a data field. That's the payload of the node. And with a linked list, a node has a reference to the next node. With a tree, I don't have one reference, but I have a whole bunch of references to the child nodes. So one way of looking at a tree is it's just like a list, except you don't have just one next pointer, but you have any number of them. At every point, it can branch off into these children. So the API here is a little bit cumbersome. To make a tree with this API, you can make a tree that is just a root that has one element, and then you can add subtrees to it. So that you can do that, we'll do this clicker question here. So follow through this and tell me what are the leaves of the tree are that you're constructing. You probably want to sketch it out on paper. Yeah. You could have, instead of having the list, you could have an iterator to it. Or you could, oh, you mean why each node could have a pointer in this direction and one in that direction, so to speak. Yeah, that's a feasible implementation. I mean, that would probably be a more efficient implementation. So I've chosen this implementation to be easy to use. It turns out it does that in 46B. There are not that many examples of general trees. And I wanted to have the one that was the simplest to press into service. All right, so let's see. So which tree is going to be the root? Well, we're starting with R, and R sounds suspiciously like the root, and we're adding subtrees S. Okay, so we're starting with R. We're adding to that S, and S gets two subtrees, T and U. So that's how the tree must look like. And T and U were here, so it must be Barney and Fred are the leaves. So let's see what everyone says. And that's what the majority did say, but about a third isn't so clear about that. So that's not so great. Close this poll. Okay. Yeah, so I'll do it one more time in slow motion for the benefit of that third. So we're starting with R, we're adding a subtree S, we're adding another subtree T, and then to S we're adding another subtree U. And that's how the tree comes up. So most tree algorithms are recursive because the formulation of a tree itself is recursive in a way. That, it's a node, and each of the children are nodes, and the grandchildren are nodes. And, well, I guess what I really should say is there are two kinds of tree algorithms that you're going to see. If you happen to have a tree algorithm that, let me get a tree here, where the computation goes along a single path. Well, that was a too short path. Let me take a longer path. If the computation happens to go along a single path, then you could make it recursive, or you could make it non-recursive. But if you have an algorithm that needs to visit all of the elements, all of them, then really the only feasible chance to make the algorithm is to do it recursively. I guess you could try to push all of the nodes into a stack and then pop them off one at a time, but that's really tedious. So essentially all of the tree algorithms that you're going to be seeing in the next few sections are recursive algorithms. And so one of the reasons that recursion is so prominent in this course is that now you really have no realistic chance to avoid it. So here is a classic example. I want to find out how many nodes do I have? What is the size of the tree? And so from the recursive point of view is I'm in this node. I have a bunch of children, each of which, start with a node, each of which are trees. And I'm asking, hey, first child, what's your size? How many nodes do you have? Second child, what's your size? Third child, what's your size? And I add up all of those sizes. That's the code that you see here. And of course, I must not forget myself. I'm contributing one node to the size. And that is my size. It is 1 plus the size of all of the children. Conceptually, I think that's simple. I hope that's simple to you. If this guy here has 4 nodes, and this one has 9 nodes, and this one has 2 nodes, and this one has 11 nodes, then the total nodes in this entire thing are 1 plus 4 plus 9 plus 12 plus 11. how does this tree here know how many nodes it has? I don't care. That's the miracle of recursion. If I had to care about every last thing, I would not be able to get out of bed in the morning. So recursively, that thing somehow knows how to compute its size. Of course, there has to be some kind of boundary case. And that would be, what if the tree is the empty tree that you find down here? If there is no root, then the tree is empty and its size is 0. Otherwise, we're asking root.size. Notice there are two functions called size, or two methods, I should say, called size. There's the method in the tree class. That's the one that the client of the tree uses. Someone who works with a tree and builds a tree, analyzes a tree, has no actual conceptual knowledge of whether the tree is made out of nodes, or like what you were suggesting, some a different implementation of the nodes that are chained in a complex way, or in any other way. So the client of a tree will only talk to the tree and never to the nodes. But for that recursive stuff, you have to get at the nodes, because at the nodes it's really recursive. A node has more nodes. A tree doesn't have more trees, but a node has nodes as children. Just like with the linked list, where a node had a next, but the linked list itself only had a pointer to the head node. So it's exactly the same thing. And we have these two functions. This function is on the level of the tree. This function here is on the level of the node. So let's put that. And notice that here I'm giving these two functions the same name. I call them size. And that's just to show to the reader of the code that those are just intimately related. You could give them the same name or not, but this is the common thing to do. So here we want to compute the height of a tree. What is the height? The height is the path, it is the longest path from the root to one of the nodes. So let's, before doing that, have a quick thing. What is the height of this tree? 6, right? It's 1, 2, 3, 4, 5, 6. Fair warning that there's an essential difference between 46b and 146. And that is in 46b, when we say the height of the tree, we count the nodes. So we say this tree has height 6. When you get into 146, they only count the edges because they use a different textbook. So just advanced warnings. But we're counting the nodes, so we say this tree has height 6. So how do you count the height of a general tree? We'll do it here where we need it. So I have a tree, so I'm looking at the root node, and I'm asking all my children, hey, how tall are you? And whatever those heights are, the only thing that matters is the height of the tallest one, right? And then I shouldn't forget myself, so this whole thing is going to be 12. So ponder this function here and see if I've done it correctly or if I've forgotten some part, and tell me in the clicker question whether it works or not. No, I don't get it. So if we look at this computation here, we're setting h to 0. And then over here, there's this funky math max of h. This is just another way of saying if child height greater than h, then h should be the child height. But of course, I don't want to write it like that. What would be bad about writing it the way I just did? That would work, but what's bad about it? Oh, this would call the method twice. Right, so if h is greater than child height, then it'll call the method one more time, and that's a potentially costly method. That method goes into all of the leaves of the tree. And do I really want the tree to say, oh, I had 1,000 children, and then say, oh, how many was that again? And it has to go through its entire set of children again. So I avoid that in this way by just passing it on to the max method. This is a generally good trick to know that if you need to compute the maximum of something. The largest one, you can progressively, instead of summing something up, you can just max things up like that. So keep that in mind next time you need to do max computation. It's a useful way of doing it. And so then I return h plus 1, y plus 1, because that's the current node itself. So let's see what people answered. We have 99 votes. And, oh, wow. Okay, so we have a beautiful progression here. Now just someone cast his vote for the majority. The majority was right. It works incorrectly for empty trees, because suppose the tree is empty, so we have an empty tree and we call height. It's going to return root.height, but for an empty tree, root is null, and you get a null pointer exception. So that's the problem. Easy enough to avoid. We say if root equals null, what's the height of an empty tree? Should be 0, right? Now in 146, the height of an empty tree is -1, which I think is weird. And so that's why I set up the height like this. All right. Okay, in the interest of time, we're going to be skipping this one here. Or not. We have time and we have no more slides. Okay, so. All right, so the majority answer is 2. That's only a slight majority. So most people say this one doesn't work for any trees. So let's see. So if it's an empty tree, then the root is 0. And what's the height of an empty tree? 0. We just talked about that. And here it says 1. So it doesn't work for empty trees. Now let's say it's a non-empty tree. And so over here it does the same thing that it did before. It computes the height of the largest subtree. So that's good. But the problem is then it just returns that. It doesn't add 1 to it. So in fact, what this function computes is it computes 0 for all non-empty trees. Think about it. It always returns 0. Because at the leaves it returns 0. Then at the next level it computes the maximum of all those zeros and returns it. And the next level after that it also does that. Yes? Where? Oh, I am. Oh, that too. Okay. Okay, yeah. I should fix that. Okay, I leave that on here so I fix it. So, last question that I don't have as a clicker question, unfortunately. That would have been a great clicker question. And okay, I'm going to make this into an impromptu clicker question. And so now I have to type in the question. What is the big O efficiency of size and height in terms of n, the number of nodes in the tree? And I'll give you a couple of exciting choices. O of log n, O of n, O of n log n, and O of n squared, which I guess I'll write like this. So imagine a tree with maybe 1,000 nodes of some shape, and now I'm calling size on that tree, or I'm calling height on that tree. How long does it take? How many steps does it take? Yeah? Oh, max is constant time. I mean, all max does is if A is less than B, return A, else return B. All right, so the majority answer says it's O of n, and that is entirely correct. So there's always a few people who say, oh, because it has to be with a tree, it should be log n or something, and that will actually get worse after the next lecture. So it is O of n, and so the way you want to imagine it is that if you have your tree here, and say this one had 100, and this one had 600, and this one had 300 children, then it really is going to take 100 steps to visit all of the children, and 600 steps to visit all of these, and 300 steps to visit all of those. And so then we visit one more. So the visiting happens once per node, and that is the cost of the operation. So for the height, it's the same thing, because you have to visit every node to compute the height. All right, we'll leave it at that.